Welcome back. We're in momentum, worksheet number 1, problem number 5. Two girls with masses of 50 kilograms and 70 kilograms are at rest on frictionless inline skates. Oh, that'd be really fun. Inline skates are pretty good, but they do have a little friction. Okay, so frictionless now in this case. The larger girl pushes the smaller girl so that the latter, the later one, the smaller one, rolls away at 10 meters per second. All right, what's the effect of the action on the large girl? Okay, all right. So maybe we got a big kid and a small kid, maybe a freshman and a senior, or maybe a bigger difference. Maybe it was like a fifth grader and a freshman, something like that. Okay. What's the effect of the action on the larger girl? And then what change momentum does each girl give the other and in which direction? Well, it partially depends on which way we draw it. So first we identify the action here, and it seems to always be helpful there. So they push one another, or you might say the larger girl pushes the other one. I think you know by now that they're both pushing each other, but if not, we'll find out. We'll do a before and after of both of these things. So I'm going to put the smaller girl on the left-hand side. I'll try to draw her smaller and the other one bigger, so don't get confused. She's gonna push her, so she's not having a good day here. She's all mean and grumpy. I'm gonna push the other girl, and that is kind of mean. Okay, so they got little roller skates on here. There's little wheels. Sorry, inline skates. Roller blades, you might say. All right, so that's before they push and then after they push. So then after they push, the larger girl pushes the smaller girl, so that the smaller girl, the latter one, the one that's stated second there, the later one, rolls away at a speed of 10 meters per second. Now, if the larger girl on the right pushes the one on the left, the little girl on the left is going to go which way? Yeah, I would agree, to the left here. So I'm going to copy this because there's no way that I'm going to be able to replicate that with some accuracy there. So then this girl, I'll put her a little bit further away. She's going to be moving this direction here with a speed of 10 meters per second, but now that's a velocity of, in our picture, negative 10 meters per second. So that's the VS for small girl, VL for large girl. And at the beginning, how fast are these things going? Well, they're going at rest here, so both the velocity of the small girl is 0 and the velocity of the large girl here is 0 as well. Okay, great. So then this is a question mark over here. Well, if large girl pushes small girl goes to the left, large girl goes to the right? Question mark. It would seem reasonable. Let's think about it from a force perspective. Large girl puts a force to the left on the small girl here, and maybe I'll kind of improperly draw here that this girl got a force going that way. But that means that the little girl is going to put a force on the big girl going that way. Oh. Hey, wait, hold on a second. Describe to me which one of these is a bigger force. Remember, the large girl pushed the small girl. Which one's bigger? Well, big girl pushes small girl to the left. Small girl then must put a force on the big girl going to the right. And this sounds like a law here. A acts on B, B acts on A. We're talking about Newton's third law here. Oh, cool. That means that these things must be the exact same amount of force, and they are. Okay, cool. Well, now if it's the same amount of force, and if you were to time this, well, let's think about that for a second. We're getting deeper into this momentum unit. If I was to time this interaction, I timed how long this large girl pushed this small girl, I'd get a value. If I had somebody else who's going to time the same thing, but they were going to time instead the small girl pushing and putting this force on the big girl, compare their times. Would they be the same? Different? Well, there's only the one push there. So it's got to be the same amount of time. Wait, now if it's the same amount of force and it's the same amount of time, then it must be the same amount of change in momentum there. Oh, cool. Okay, so wait, hold on. Get my notes straight. This is Newton's third law there. This is Newton's third law here, but it's actually pretty similar. Anyways, so that means that the force is the same for both of these, and the time, you said, is going to be the same for both of these. So then each girl is going to have the same change in momentum. Wait, okay, Mr. Wishwait. Let's go and do this problem and see if that's really true or not. We'll choose a system here. I'll do it the same as before. I'll make it everything that's interacting here. So I'll make it both the small and large girl. So I'll make them small and large. And so then I know that the change in momentum of everything that's interacting must be 0, or the momentum of the beforehand must be equal to the momentum afterwards. What momentum do I have before? Well, it's the momentum of that small girl at the beginning and the momentum of the large girl at the beginning. And it's equal to the momentum of the small girl afterwards and the momentum of the large girl afterwards. Well, I know some of these values. We said that they're moving how fast at the beginning? 0. Well, 0 times any mass is just 0 times any mass is just 0. So I have a big fat 0 over there. And then afterwards here, what do I know afterwards? Well, I know that the little girl in this case is going to be moving and moving to the left here. So what do I know? It's 50 and 70 for the masses, right? Yeah. So I know that this is the mass of the small girl times the velocity of that small girl, and the mass of the large girl times the velocity of the large girl. And I know some of these values here. So this is 50 times -10 plus 70 times, I don't know her velocity there. And that's -10 because she was moving to the left in our picture. And so now if I go and I solve this, I can solve this for the velocity of the large girl. And when I go and do that, I get 500 divided by 70, because I got to move that over to the other side, so I got to add it over there. And so I get 7.14 meters per second is the velocity of that large girl. And does that make sense? Okay, so large girl pushes small girl's moving fast. She is going to get kicked back a little bit because she's got this force on her as well. And then she's going to be moving to the right, but it's not going to be going as fast. Does that make sense? Oh, yeah. It's some really massive object pushes a less massive object, and so the one that's less massive is going to be moving faster than the one that's more massive. Does that make sense from this kind of Newton's third law extension here? Well, yeah, we said the change in momentum of each one has to be the same. And if the change in momentum has to be the same, well then they have different masses. This one's got to have a bigger velocity, so it multiplies by our mass, to get the same value as this bigger mass, and then therefore has to be multiplied by a smaller velocity so that they get the same amount. And notice we actually see that right here in the calculations. We said that this bit plus that bit has to add up to be 0. Well, then that means that this multiplication there has to be the same value as that multiplication there. Here we got a small thing, and then it has to be, and it's multiplied by a relatively large thing. Now a larger thing, and then it's got to be multiplied by a smaller thing so that it gets the same value. Okay, cool. So that does seem to make sense. So what what is the effect of the action on the larger girl? Well, we just solved that. She's moving now to the right-hand side at a slower speed than the small girl. What change in momentum does each girl give the other, and in which direction? Oh, okay. Well, we actually kind of calculated that already. Let's do that step by step, day by day by day. I'm sure nobody else knows the old TV show from the 90s, Step by Step. Go look up that intro song. That one's a fun one. Okay. If you go look that up, the actual, at the end there, they show a roller coaster going along. That's Great America's American Eagle in Chicago there. And they superimposed it next to the ocean there because I think the show took place in California, maybe San Diego or something like that. Anyways, so yeah, so this is the change in momentum of anything is just the ending minus the beginning. And so now if I go do that for the change in momentum of that small girl, let's say, that's the ending momentum of the small girl minus the beginning momentum of the small girl. Well, excuse me, we already know the beginning momentum of the small girl. That was 0. That makes that one a little bit easy. So now the change in momentum of the small girl and the same thing is going to be true for the large girl because that's 0 at the beginning as well, is just actually the ending momentum. And the ending momentum here was just the 50 times -10, so that's -500. And let's go put the units on that. That's kilograms meters per second. We showed that in 2 videos ago. That was problem number, what are we on, 6? Yeah, so that was problem 4, I think we did all those units on. So that's the change in momentum of that small girl. Notice it's negative. Why is it negative? Oh, that's right. Momentum has a direction because the velocity's got a direction, right? And the momentum is pointing which way? Oh, it's pointing to the left. Right, that would be a negative direction. Correct, that would be a negative direction would be a better way to say that. And now if I go and do a similar thing, but I'm going to go and do that for, let me line that up there. I'm going to go do that for the large girl. That's the momentum of the large girl at the end minus the momentum of the large girl at the beginning, and that thing was 0, as we said. And so now it's just 70 times 7.14, and as we can see from the algebra here, it's got to be the exact same value, except it's positive, kilograms meters per second. Does that make sense for our problem here? This change in momentum of the large girl. Well, that momentum means that she's going to start moving to the right-hand side because it's change in momentum, and sure enough, that's what we expected to happen, and that's actually what did happen. Cool. Great. That's it. Have a beautiful day.